Hi everyone, I'm Nick Karpowitz from the Max Planck Institute of Quantum Optics. So I make a nonlinear optics simulation called Lightwave Explorer, and I just released a new version of it. So I thought I'd make a quick video to talk about the new features inside. Most of the changes are under the hood, let's say. If you look at the big pull request I made on the repository, there's more lines removed than added. But there is one big user-facing feature, which is the ability to control your beam mode. And I thought I'd give us a bit of an overview on how to do this. So I set up a basic test simulation here, just with one broadband pulse focused in vacuum, because we don't want to do any nonlinear optics at the moment. We're just controlling the input pulse. And since we're controlling the mode, the really interesting part is going to be this beam view. So I'm going to turn off everything else, and we're going to look at the near field distribution of the light. So this is what we would normally send in to the beam in the previous versions of the software, just a TM00 mode. Now we have the ability, using these pull downs and this box here, to enter a more detailed beam. We can describe it in a basis of Laguerre-Gauss or Hermite-Gauss modes, and we can add quite a few of these and also control different parameters of each individual mode. So let's just have a look at how this looks if we use Laguerre-Gauss mode, a bit higher order. So Laguerre-Gauss modes have two parameters, P and L. P you can think of as adding rings around the beam, and L makes the wavefront into a vortex. So we'll start with the 1, 0 mode. There are two more parameters that we need to describe for each mode that we use: a weight and a phase. If you just have one mode, it doesn't really matter because it gets normalized to the right energy anyway, but you'll see where these can come in later. So we're going to put in a 1, 0 mode, and you can see now we have P equals to 1, so we have a ring around the beam, and we don't have any L yet. We can now look at what happens if we have a higher order mode. So 3, 2, 1, let's say. So P is equal to 3, L is equal to 2, and this gives us more rings and also a node in the center. The effect of L in terms of the intensity distribution is fairly subtle. It's mostly working on the phase. So I said it makes this vortex-like phase. We can make phase visible just by creating a superposition of modes. So we'll put on top of this 3, 2 mode, put in the 0, 0 mode with the same weight, and it'll be in phase. And you can see some structure there. It gets more interesting if we let it propagate. So what happens when we let it propagate? You'll see it kind of spins around. You can start to imagine now why these Laguerre-Gauss modes are said to have a orbital angular momentum associated with them. If we change the sign of this L parameter of the beam, you'll see it looks almost the same, but it rotates in the opposite direction. You can play around with that. We can go to even higher order if we want. Maybe not that high, but you can see they get more and more complicated as you go to higher order. We also have the Hermite-Gauss modes available to us, so we can have a look at how these look. So let's go to the 1, 0 mode. It has a line down the center. Turn off the propagation for now. It has a line down the center, and if we go to 0, 1, the line is in the other direction. So the Laguerre-Gauss modes are good if you have, let's say, radially symmetric distortions. They're efficient for describing things like spherical aberration or so on. The Hermite-Gauss modes are more useful if you want to describe something that's more Cartesian in nature, right? And if we want to go to higher order, you can see how these look. Like there's the 4, 4 mode. Now when I let these propagate, you'll notice that if you have a single mode, it maintains its shape. You can see the different colors spread out as it propagates because it's broadband pulse. So the red diffracts faster than the blue away from the focus. But otherwise you maintain the same shape. It's only when you have a superposition that you'll start to see the shape change with propagation. We can do more than just describe the spatial shape in a superposition of modes. In principle, each one of these is a complete basis, so we can describe fairly arbitrary shapes, but sometimes we also want to apply offsets and things like that to different parts of the mode. To do that, we have additional parameters available to us. So if I open up this sheet here, we can do a basic offset of the beam by adding a few parameters after. Actually, let me show this. I will put all of these in the description of the video as well if you want to copy paste some of these different examples. The first 4 parameters we have here are describing our basic mode, and it's followed by another 7. These 7 parameters are offsets to the beam waist, the rotation of the beam, its position in X, Y, and Z, and 2 angles, left and right and up and down. So we can add offsets to all of these modes individually just by putting these numbers afterwards. So in this case, we have a X offset of 50. Let's just go to Laguerre, and I'll turn off the propagation just so it's easier to see. All right, so we just shifted it 50 microns in the X direction. We can do minus 50, right? We can just control the position of each one of these individual modes. This by itself is kind of useful, but we can also describe more complicated distortions of our beams by making these offsets frequency dependent. The next thing that we can do is add another row, 7 parameters, and these will describe a Taylor series expansion in frequency using units of microns and terahertz because they're convenient for this kind of thing. What I'm going to do here is I'm going to make the Z position of the beam, so essentially where the beam is focusing relative to the starting plane of the simulation, depend on frequency. And this is going to emulate the effect of having chromatic aberration. So I'll put this in here. The main thing you see is the beam is discolored, right? And if I change my observation plane, you'll see that it changes color by the position of the observation plane. The on-axis light is more dominated by a given color just because the different colors are focusing in different positions due to the effects of chromatic aberration. We can also add another term in this Taylor series expansion. We can keep going up to third order if we want. So we can add a nonlinear chromatic aberration. Nonlinear in the sense of the focus in this case depends quadratically on frequency. So if I put this beam description into here, you can see it's a lot of numbers in a tiny box. I want to work on the user interface on this a little bit later, but I wanted to get the sort of basic feature out for people to use. If you have suggestions for how to make this UI more convenient, feel free to leave a comment. But what I'm going to do now is I'm going to give a quadratic dependence of the focal position on frequency. And you'll see here that the beam is kind of greenish because the center frequency is kind of greenish, and it's just surrounded by a bit of a purple cloud of all of the red and the blue components that aren't sharing that same focus. We can also make our offsets of the beam spatially dependent, right? So we can have a spatial chirp in the near field. It'll look something like this, right? So we have a quadratic chirp in the Y direction, linear chirp in the X direction. So you end up with this kind of parabolic rainbow. And we can also do this in the far field if we want to as well, just by adding a chirp to the angle. So if I look at this in the near field, all the colors are still together. But if I go to the far field, you'll see they're all going to eventually spread out. So now you have a pretty big parameter space to control for the input beam of your simulation. So I hope this allows you to better match your experimental conditions and end up with kind of a nicer agreement between theory and experiment, or make better predictions about how your laser is going to work in a future experiment. So that's it for today. I hope this is useful. Subscribe for future updates and have a good day.